So today what we're going to try to do is actually test that assumption quantitatively and show a little bit about ways in which we can model flexibility on projects to actually determine what kinds of flexibility yields what kinds of value. To do this, we are going to use some teaching material which I have not created, but it was created at MIT by professor called Richard de Neufel, who works a lot on flexibility in infrastructure. He's part of the engineering systems group, I believe, at MIT, or was. I think he's more or less retired now. And when I met Richard a few years ago and I said, look, you have wonderful material, he said, please feel free to steal it from me. Okay, so true to his wishes, we are actually taking his material. It's all available publicly anyway. So, and we're going to use that because it's a very nicely done case. Okay, so let's just first look at the case itself. So let me sort of explain a few things to you. The issue at hand here is that you're going to build a plant that manufactures something, right? We don't know what you can imagine. You can use your imagination to figure out whatever that something is based on what you want it to be. But there are two options. So if you look here, right, there is an option of building a big plant. Okay, this big plant will produce 900,000 units a year. All right. And the price of each unit, as you can see, is about $2,000 a unit. Okay, so the big plant produces $900,000 units a year. On the other hand, there's a small plant. The small plant can only produce 300,000 units a year, but you have the ability to build multiple small plants if you like. All right. So essentially, you have two strategies. One is you build a large plant, right? The second is you build multiple small plants. Okay. There is also some expectation on demand, right, and demand is going to increase as time goes on. All right. So this is fundamentally the situation. When you start looking at costs, the cost of building the big plant is $900 million. The cost of building the small plant is $300 million, right? So it's proportional. $300 million plant manufactures 300,000 units. $900 million plant manufactures 900,000 units, right? The change is on the variable cost, right? The fixed costs are roughly proportional. With regards to variable costs, right, the big plant variable costs are $1,280 per unit, all right, whereas the small plant actually costs a bit more, $1,500 a unit, all right, possibly because there are economies of scale at play. Right, so you have a big plant with you have much more material going in. You're probably able to amortize that material across a number of processes. You have what we call economies of scale as you get larger volume production, and therefore maybe the costs come down. Right, so you have two options: big plant, small plant. Right, big plant produces more, small plant doesn't produce that much. Big plant actually costs less to operate, small plant costs a little bit more to operate. And you also have this demand variable where demand is slowly going to increase, okay, over 3 years. Now let's say you have a 3-year horizon. Intuitively, would you rather pick a big plant or would you rather pick the small plants? Okay, intuitively, what do you guys feel like doing? 3 years, let's just take a 3-year horizon for now. We're just looking at 3-year horizon. Would you guys rather build a big plant or would you guys rather build small plants? Small plants, okay, intuitively. And what would you, how would you go about building your small plants? Right, would you build all 3 of your small plants in the first year? Right, what do you think would be a good strategy for you? So with increase in demand, you will start increasing the plant. So given that the demand is 300, 600, 900, what is likely to be your small plant strategy? So you will do one plant. First year you will build one plant, second year you will build the second plant, third year you will build the third plant, right? That way you don't have to spend $900 million upfront. You can spend 300 this year, 300 next year, 300 the year after, etc. Right? So that's intuitive. Now let's just do a calculation to figure out which one actually is a better option given these numbers, right? I've also given discount rates. Option A has a discount rate of 9%, option B has a discount rate of 8%. We'll play with these a little bit, right? But option B seems to be a bit of a safer option, so slightly lesser discount rate, all of that, all right? So let's go to the Plan A data sheet. So one of the things we want to do is get to each of these has to now be zoomed. Okay, one of the things we want to do is also figure out ways in which we are, we can use Excel in a neat fashion. And one of the ways in which you use Excel to build these models is you actually have an assumption sheet where you put all your assumptions and then you draw from those assumptions as you do your calculations, right? Therefore, what happens, so this sheet, entry sheet, has most of my assumptions, right? Every time, whether it's plan A or whether it's plan B, every time I want to draw from an assumption, right, I go to the entry sheet. The reason is if I need to change something, right, if demand changes, right, it's not 300, 600, 900, it's 4,000, 400, 800, 1,200. I just change it here once in this entry sheet, and that will then be reflected on all my other spreadsheets because I'm referring to the main sheet, right? So that's just good practice, okay? So using that, let's sort of, okay, look at the large plant option and how we would model it, all right? So we have year 0, year 1, year 2, and year 3, right? What happens in year 0? Essentially, nothing much seems to happen in year 0. Year 1, essentially we build one plant, okay? So I'm going to go to this, so we have start filling this as we go along. So the number of plants in year 1 is 1, okay? That's clear, all right? Therefore, what is the capacity of production in year 1? 900, right? The big plant can build 900, okay? So I'm going to go to this slide. When you say capacity, I'm going to say equal to, if I can find the equal to, there we are, the equal to, go to the entry sheet and look and click on this cell D14, which is the capacity of the big plant, right? And I click enter. So the capacity at the year 1 is I have one plant, and therefore it is the capacity of that one plant, right? Technically, it should actually be, it should actually be this multiplied by the number of plants I have. Each plant has 900 unit capacity, and therefore in year 1 I have 900 units times one plant because I have one plant at the end of the year, okay? What is the demand? Demand is 300. Where do I get this from? Again, I say equal to, I go to this sheet, and I just click on the demand in the first year. So the demand is 300,000 units, all right? So my demand is 300, my capacity of production is 900. How much do I actually produce? 300, right? Because 300 is the demand, right? So I have a capacity to produce 900, but I don't produce that much, right? So here in this cell, I say equal to, and then I use this function called minimum, right? I say min, open bracket, and I just select both of these cells, E4 colon E5, or if you just select both of these cells, you close the bracket, press enter, right? Essentially, it takes the minimum of of both, right? So I'm putting this in formulaically because tomorrow, or whatever, in half an hour, if I want to change these demand estimates and production estimates, all I need to do is change my assumptions, the entry sheet, and the rest will automatically change, right? So the formula is how much am I producing is a function of the minimum of what's required and what capacity I have. Tomorrow, if you say produce 1,200 units, I'll only produce 900 because that's my capacity, okay? What's the unit price? That's already given. So the unit price of all of this is, where's the unit price? Is $2,000 a unit, okay? So that's a given. And therefore, what is the revenue that I'm making? What's the revenue that I'm making in year 1? The revenue that I expect to make? Right? So essentially, I say equal to the unit price, or sorry, the production multiplied by the unit price, or unit price multiplied by the production, right? So I'm producing 300, I'm getting 2 for each, and therefore I'm going to get $600,000. All right? Okay. So the unit variable cost, which is row 9, that's easy as well because that's already there. The unit variable cost for the big plant is 1.28, right? And therefore the question is, what is the total variable cost? So I'm going to get $600,000, right, in terms of revenue. What is my total variable cost? My total variable cost is the amount I'm producing multiplied by the variable cost per unit, right? So the variable cost per unit is 1.28, and I'm producing 300,000 units, right? So this is my overall variable cost. My unit variable cost was 1.28. My overall variable cost is 384 because I'm producing 300. All right. Tomorrow, if I chose to produce 400 or 450, then my overall variable cost will go up. Okay. with regards to my investment, so the way this spreadsheet has already worked is by saying that I have a plant in year 1 to produce, I've already invested at t equals 0, right? So t equals 0, I invested the plant, and therefore it's now producing something for me. So my investment at the point is 0. There is probably, I can probably do this formulaically as well, where essentially what I would do is I would say it's the cost of a plant. So in other words, if I'm going to make any investment now, it's investment for the following year. Okay. So the way I would do that is I would say this is equal to what's the cost of the plant, right? It's $900 million multiplied by and I'll open brackets, the amount of capacity I need next year minus the capacity that I already have this year, right? So essentially I'm saying, look, if I choose to expand, then I have to invest for that expansion now. So if I wanted 2 plants next year, right, and I have 1 plant this year, then 2 minus 1, I need 1 more plant, and that will cost me another 900. But in the current scenario, I have 1 plant this year, I only have 1 plant next year, I'm not investing any, right? So the answer is 0, but I'm doing it formulaically, because tomorrow I can go ahead and change these assumptions, right? I can go ahead and change number of plants. I can say this is 2, and the moment I say this is 2, those numbers change. Okay. All right. Salvage, it's a good question. There was some salvage data here below. Salvage for plan A, there's no salvage, and plan B, there was a salvage. That makes plan A even better. Okay. And then the question is, what is therefore the net value or revenue or whatever that I'm getting this year, right? So the net value or revenue I'm getting this year is the sum of all the inflows. So the inflows are revenue, and the inflows are also salvage. Of course, I'm getting no salvage, but that's still an inflow. Okay. And my outflows are my variable cost, which is 384, and the investment, which happens to be 0. But if I were to invest, then that would be an expense, right? So E8 and E12 are my inflows, right? Revenue and salvage. E10 and E11 are my outflows, right? Variable cost and capital cost, right? So we should all get 260. Okay. Now this is happening in year 1, so I have to start discounting it, right? It was a 9% discount rate. So how much should I discount all of my cash flows at the end of year 1? What is the formula? Right, so should I just add up 216 and 432 and 648 and 900? Obviously I can't, right, because I have to discount them. By how much do I discount 216? At a 9% interest rate, what would be the discount factor? 1.09, right, because it's 1 year out, right? The 432 is getting discounted 1.09 square. The 648 is getting discounted 1.09 cube, right? So this discount factor, again, I'm just going to put it in a formula. It's 1 divided by it's 1 by 1 plus r raised to n, right? R is 9% and n is 1. So I'm just going to put it formulaically. 1 plus r, let's find the r here. 1 plus r and exponent, which is the caret above the 6, the number 6 on your keyboard, n, which is the year here. Okay. So essentially I've done 1 by 1.09, right? So 1 by 1.09, we can even check it here, equals 1 by 1.09 is 0.91743, right? It's exactly the same thing. I've just done it to make us, just done it formulaically, all right? So therefore, this 216, the present value of that 216 is how much? So 216 multiplied by 0.91, which is 1 by 0.09. So let me just multiply these two. Right, which is 198. So the present value, so I'm making 216 rupees next year, but in today's terms that's 198 because I'm applying a 9% discount factor. So in a 3-year horizon, I'm spending 900 rupees the first year, I'm making 216, 432 and 648 in 3 years, but of course those future cash flows are getting discounted. So actually the 900 remains 900, but 216 becomes 198, 432 becomes 363, 648 becomes 500 because I'm discounting it. So my overall net present value, right, will be the sum of all of these discounted cash flows because I've already discounted them. So now I can add them, right? So I've already discounted them. So I get 162.1. Okay, you all should get 162.1. This is completely deterministic, right? Everyone needs to get 162.1. So do you all have 162.1? Shut this off. Sorry, I think this is what is causing the interference. Yeah. No, the salvage value will be calculated. Yeah, so if you look at the salvage value, it's really there. Yeah, so it depends on whether you are going to get rid of the plant. And in fact, if you look at the explanation, it says the salvage value which only occurs in year 3. So the input is, in fact, I probably don't even have to do this formula. You're right. I think I should just put in a physical 0 there. So only in the final year? Yeah, because only in the final year I'll get the salvage, right? So even if there was a salvage, right, I should have just put in, I mean, it's just a 0 because I'm not selling the plant here. Okay, 216, sorry, 162.1. Who doesn't get 162.1? Okay, everyone gets 162. Okay, now let's go back to the entries sheet and do. So if you go to plan B, you will find that this has already been done for you, right? So if you go to the plan B sheet, it's already been done for us, right? So let's go back to the entries sheet, and in row 31, it says difference between NPV A and NPV B, right? Let's just say find out what the difference is. So I'm going to say equal to NPV A, select that cell, minus NPV B. Right. So in other words, it's 5.66, right. So I'm just subtracting. We got 162.1. We had already calculated, the people who had prepared the spreadsheet had already calculated plan B, and they had 156.5. So I'm just subtracting the two, right. So I get a net NPV difference of 5.66. Right, just plan A NPV minus plan B NPV, just selecting this cell minus that cell. Make sure you put the equal to in front. Who's not getting 5.66? Everyone's good? What does this mean? So at the moment, it looks like plan A is better than plan B, right? I'm getting a slightly higher net present value with regards to plan A. So even though plan B was modular, and all of that, and even though it had a salvage value and all of these kinds of things, which was taken into account in that spreadsheet, the fact of the matter is that plan A ends up working out much better. Yeah.
So in the plan B, the salvage value has been mentioned as 300. Like it is just for one plant.
Yeah, I think so that the entries assumption, the salvage value is not per plant, it is per plan. Right. So the plan B salvage is 300. So at the end of the 3rd year, when you sell all your plants, you get 300. Okay. But if you look at plan B, you will find that, so they've done this assumption, right. So in the first year there's 1 plant, in the second year there's 2 plants, in the 3rd year there's a 3rd plant. So they've added plants incrementally. So they've not spent 900 upfront, they've spent 300, but still they're not making a big profit, maybe because the variable costs of plant B are higher. Right. So whatever. So at the moment, plant A is better than plan A is better than plan B. All right. Okay. So now the first thing we can do is do a little bit of. So everyone's okay here. We're all on the same page, right? Because the problem is if you get left behind, you'll never catch up, right? So if you're not there, we can take a moment. We can pause. So everyone's okay. All right. Okay. So this is just the baseline. Where are you guys stuck? All good? Okay. So now, one of the things that people might, we might sort of worry is, okay, how sensitive is all of this? What happens if the, the variable cost was a little bit different, right? Whether it was a little bit higher for plan A or plan B, whatever it is. What happens if the discount rate I changed a little bit, right? Instead of 8%, what if it was 7.8%? So Excel offers us very easy ways to start looking at how to do sensitivity analysis, right? So there are these data tables that you can use. So if you just scroll down the entry sheet a little bit, you'll see something like this, right? You'll see a one-way data table. Okay. So here, what we want to do is in this yellow box here, we're going to again calculate the difference in NPVs, right? So because that's what tells me which is better or not. So I'm going to put in the same formula here, right? I'm going to say NPVA minus NPVB. So I'm going to get that same 5.66 here. I'm going to say NPVA minus NPVB. All right. So I get my 5.66 there also. All right. And here in this column are the various discount rates for plan B that I want to do some sensitivity on, right? So plan B had a discount rate of 8%, but I'm saying what happens if I went from 8 to 10% or whatever range, right? So the way to do this is if you just select both of these cells, right, and then you drag the whole thing all the way down till the end of the yellow, right, you'll find that Excel just continues with the same progression. Right? If you took just one cell and dragged it down, then Excel would have put 10% everywhere. If you take two cells and you drag them down, because one is 10 and the other is 9.9, Excel does the same thing. So you go 9.8, 9.7, you can also type it in if you like, but right. So essentially the point is I am going to do a sensitivity on all of these. In other words, I'm going to calculate NPVA minus NPVB, right, but with discount rates at 8, 8.1, 8.2, 8.3, 8.4, etc. right. So the way I do this, right, is essentially using what we call a data table, right. So this is what I want you to do. I want you to select this whole block, both rows and columns, right, select the whole block. And then you go to, most likely it will be in data, right. Within data, you should have something that says what if analysis, right, irrespective of which version you're using, something like that. And within what if analysis, there's something called data table. All right. So if you click that, you'll see a dialog box like this coming up, right. So this is what we call a column based data table, right, because it's my data on the column that's varying, right. So forget the row input cell, right, the column input cell, right, is the cell that I am varying. What is the cell that I'm varying? What is the parameter I'm varying? No, what is the name of the parameter? It's the discount rate, right? The discount rate is here, right on top. This is the discount rate for plan B, right? So what I'm saying is I want to vary that parameter, right? So what this means is I'm varying that parameter, right, the discount rate for plan B. I'm varying it 10, 9.9, 9.8, 9.7, whatever up to 8. And for all of these variations, calculate NPVA minus NPVB. Okay. So if I say OK, then I should get something like this. Right. Again, all of you should get the same thing, right, because it's just a calculation. Right? There's no randomization, no uncertainty. Right. So in other words, I've done a sensitivity, right, and I found out that if plan B's interest rate increases, the differential between A and B keeps increasing. Right. So, to the point where if plan B's discount rate is 10%, the NPV of A is more advantageous by 35.02. Right. Are you guys able to get the data table? Right. We're able to select all of those, right, go to the data table and sort of say column, the column input cell I'm varying is the plan B discount rate, recalculate NPVA minus NPVB. Okay, let me know if you're still working on it. Just raise your hand, because if not, we'll go to the next step. Yeah. Okay, so and you have all of this on the left, that it goes 10%, whatever, 9%, etc. And did you select exactly this rectangle, starting from plan B discount rate, the 2 columns down. Okay, just try hitting F9. We've had this problem before. There are some, I don't know why, some versions of Excel loaded on some people's computer doesn't seem to work. Let's try again, hit F9. Sunoj, Arvind, you guys are, there's 5.66 again. Yes, just try it one more time. Hit F9 and see if there's a change. Which F9 worked? Yeah, just hit F9. It's a recalculation function, so sometimes it, so yeah. So now F9 worked? Okay, just check, are you selecting exactly this rectangle? Right, all the way down, right? And did you put in the column input cell? Okay, and the column input cell was that, right? And you're getting 5.66 everywhere. And if you hit F9, nothing changes. Okay, well, hopefully that's fine. I mean, it's not critical because we're not going to use this very much, but yeah, sometimes it happens. So this is essentially varying one parameter, but Excel also allows you to vary 2 parameters. Right, so one of our hypotheses for why A was better than B is we felt that A's variable cost was more advantageous to B. So what if A's variable costs and B's variable costs could be changed a little bit? What happened if one came down a bit, one came up a bit? At what point might you get a break even, right? So essentially you have here, if you scroll down a little bit more, you have something called a two-way data table, right? And the two-way data table, as you can see on the column, I'm having the variable cost for plant A and I'm varying it from 1.2 to 1.45. The actual cost we took was 1.28, but I'm varying it from 1.2 to 1.45. And on the row, I'm varying the small plant variable cost from, so it was 1.5, I'm varying it from 1.4 to 1.6, right? So I'm varying these costs a little bit. So I'm doing some sensitivity analysis on my model, okay? So again, the way I calculate all of this simultaneously is pick the entire yellow box. Okay, so I pick the entire yellow box. Okay, I do the same thing. I go to what if analysis data table. Now this is a two-way data table. The row input cell is the unit, the variable cost for the small plant. The column input cell is the variable cost for the big plant. Okay, and I just say okay. And I should see something like this. Okay, so just select the whole table, right, starting from that red box up till the end, right, and then you select that whole. So the what you've entered in the red box is what it's calculating, right. So the red box, if you click on the red box, you'll see that it's plan A C16 minus plan C B C16, which is the NPVs. So it's recalculating that by varying both of these parameters, right, simultaneous. So you get all the combinations. So if there's 20 by 20, there's 400 cells there. Right, and then you can start looking at, there are also goal seek, under the what if analysis, there are also goal seek functions, right, where it tries to say, look, can you set a particular value variable to 0 and calculate at what value should another variable take for this to become 0, etc. But you can sort of eyeball this and you can start looking at where you might start getting to the zeros. Right, so maybe at a big plant variable cost of 1.25 and a small plant variable cost of 1.465, you know, I might come to a 0. So you can figure out what your break-even points are. At what point does it make sense to use the small plant, right, with regards to this. Okay, everyone able to get something like this? All right. So this is the kind of analysis that most consultants do. Okay, so I've developed a spreadsheet, I've come up with a net present value, and then I do some sensitivities, right? I take one variable and I say, oh, what if it isn't 8%, what if it is 9%, right? And I do multiple, or I can vary two simultaneously, okay? And then I can maybe make some decisions. I think later on, I'm not sure if this is automatically there, but you can, if you just copy all of these entries, you can even graph them. I think if you yeah, so you can even graph them and see all of that, all right. But what we want to do is, but this assumes a relatively static universe, right? It assumes that whatever, I mean, of course, we've done some sensitivity, but it assumes relative statisticity with regards to stasis with regards to demand and so on, right? So we want to go up one more level and start introducing some uncertainty into our models, okay? So for that, what I want you guys to do is I want you to get out of this spreadsheet. Okay, and open 2-1, right? So get out of 1-1 and open 2-1. 1-1 is just essentially what consultants do, right? Build a model, do some sensitivity, come up with analysis, but there's really no randomization in the model, okay? Okay, let me know when you've opened up 2-1. How are we doing on 2-1? Everyone's open? Anyone not open? Raise your hands. Okay, everyone's got 2-1. Okay. Now here what we're going to do is we're going to say, look, how do you know that demand will be 300, 600, 900? Okay. What if demand was a bit variable? What was not, and variable not in terms of these nice increments. What if it was random, right? What if you couldn't really predict it? Okay. So one way of doing that is if you click on the RAND tab, right, is using something called a RAND function that Excel has. Okay. So the RAND function allows you to sort of very randomly generates random numbers between 0 and 1. Okay. So what I want to do now is if you go back to the entry spreadsheet, right now you see an uncertain factor of 50% of the expectation. Okay. So what I want to do, so what I mean by that is, I mean that in the first year, my mean is 300, but there's a 50% deviation either way. In other words, the actual demand can be anywhere between 150 and 450, right? Second year, the mean is 600, but it can be anywhere between 300 and 900, right? 50% this way, 50% that way. Third year, it's 900 is the mean, but of the distribution, but it could be anywhere between 450 and 1350, right? So my demand now has a range, right? Because I can't really predict accurate demand in real life. Okay. So what I want to do now is I want to have, rather than just taking 300, 600, 900, I want to randomly generate a demand within those bounds. Okay. And the formula for doing that is, quite simple. Use essentially, well, the formula is here, but the way you interpret that formula is you take the lower bound, okay, then you take the, so the lower bound, say for year 1, the lower bound was 150, right? So we said the demand could be anywhere between 150 and 450. So you take 150, all right, as one parameter, then you take the difference or your band, which is 300, right? You generate a random number between 0 and 1, okay, and multiply that with 300. So you get some number between 0 and 300, right? I generate a random number between 0 and 1. I multiply it with 300. So I get some number between 0 and 300. I add 150 onto it, right? So I have my 150, which is my starting point. From that starting point, I pick a random number between 0 and 300, right? So if the random generator generates a 0, my answer will be 150. If the random generator gives me a 1, the answer will be 450, right? Or if the random number generator gives me a 0.73 or a 0.67 or whatever, I'll get some random number between 150 and 450, right? Which is essentially what we are seeing in this formula. The entries at C9, right, is, what is entries at C9? Yeah, so entries at C9 is 300. And what we are saying is, okay, take the entries and, well, you can work it out, but essentially it works out to the to the same thing. So it says takes entries by C9, multiplied by 50%, so you get your 150, and then from that 150 sample, right? So one of the things you can do is, I mean, if you're too lazy to type, just cut and paste the same thing. So say Control C, go to this cell, say equal to, and Control V. Okay, so you get a random number, right? You should get a random number somewhere between 150 and 450, right? And this random number, by the way, will be different for each one of us, right? Because the random number that it generates is probably this, tied to, the time on your clock, and then some permutation, manipulation of mutation of that sequence or whatever it is, right? So each of us will get a different number. The only thing is all our numbers should be somewhere between 150 and 450, right? So I can do the same thing for cell 2 and cell 3, right? Now the two differences are, I mean, I can drag that in. For cell 2, it's actually not C9, it's C10, right? The base value that I was trying to sort of work off is C10, and the entries of C25 is the same for both, for all, because that's the 50% factor. So in other words, it's the same formula for all three cells, except that it is entries of C9, entries of C10, and entries C11, right? So for the first year, I'm taking entries at 39, which is my 300, and I'm randomizing around that. Year 2, I'm taking entries at 310, which is 600, I'm randomizing around that. Yeah, so 1 minus entries at C25 is 50%. So I take my entries of C9 multiplied by 50%, right? So I get my base of 150 or 300 or whatever. And then I sort of take that 50% multiplied by 2, I multiplied, which is essentially 1, I multiplied by some random number, right? And I then take that random number and so add it, so the product of the random number and the mean entry, I then take and add it to the initial starting point to get my random number. So it's the same sort of logic, okay? So essentially what we've done is we've now randomized demand. So it's now 311, 583.569 and 748.947. It's not a very nice and clear 300, 600, 900. Okay, first year it's a bit higher than expected. Year 2 and year 3 it's a bit lower than expected, right? So if I click enter, good. So all I have to do is click and enter, and it recalculates. Okay, and you guys can play with it. You can do F9s as much as you like until your finger starts paining, and you'll get new random generations. Okay, now and it'll all be different for all of us.